For the past few months, I've been working on developing an operating system. No, we talked about this. I don't want to see him. Get him out of here. Thank you. I've been working on developing an operating system. And so far, my operating system works on a virtual board called Virt, which itself runs on an emulator called QEMU. And for example, whenever I wanted to implement a GPU in order to have something on the screen on my operating system, I could just use a GPU that conformed to the Virt.io spec. And the good thing about this Virt.io spec is a lot of devices on QEMU conform to it, which means I was able to write a certain group of functions that would work for a lot of these devices. They also work in a pretty similar way because they're not real hardware devices with all their quirks and problems. They're just virtual devices. But I don't want my operating system to run on a virtual device forever. I want it to run on a Raspberry Pi. And that means we're not going to have access to the Virt.io GPU or even any Virt.io devices anymore. Now I'm going to have to write real drivers for real devices. Well, okay, I'm actually still doing this on QEMU. I will be doing it on a Raspberry Pi, but this is an intermediate step between the two. Now, the Raspberry Pi actually has its own GPU and its own set of peripherals. And the closest thing I have to documentation here is just the spec for the Raspberry Pi's peripherals. Now, when it comes to QEMU and the Raspberry Pi, as a matter of fact, QEMU emulates the Raspberry Pi 4B. And while this is a pretty modern Raspberry Pi, the latest Raspberry Pi is actually the Raspberry Pi 5. And if there's one lesson that I have learned when it comes to buying hardware, always buy the latest version. So I will be adapting my code to the Raspberry Pi 4B because I'm going to be running it on QEMU, but when I actually run it on real hardware, I will be running it on a Raspberry Pi 5. Now, luckily, the change between a 4B and a 5 is not that big, so most of my code will be okay, but I will need to adapt a few things. So let's start with something easy, MMIO. So in the Virt machine, we have been using something called PCI. Not this again. PCI. And PCI is a bus standard, a way that we can talk to peripherals connected to our board. And as a matter of fact, I created some functions that look like this that allow me to search for a PCI device if I know its vendor and its device ID. So whenever I'm looking, for example, for the Virt.io GPU, I can just look for the Virt.io vendor ID and the GPU's vendor ID. But on the Raspberry Pi, it's not going to be this easy. I do think the Raspberry Pi has some PCIe slots, but in order to communicate with the actual peripherals that are connected to the Raspberry Pi, such as the GPU, the USB ports, we are going to need to do it some other way. PCI is not going to be an option. For now, what I'm doing is just hard coding the base address at which these devices can be found. This is called MMIO or Memory Mapped I/O, and in this system, each peripheral on the Raspberry Pi is mapped to a specific area in memory. The address that I'm showing here is the base of the MMIO. Each device is then going to be at a different offset within this base. And this base changes depending on which device you're on, but the offsets don't tend to change, which is why we use a base and an offset. Now, there is technically a better way to do this, and that's through a device tree blob, which is a structure that we can access in order to know what our board looks like, all the peripherals, where they're mapped, what they do, and a lot of other useful information. And technically, I do have support for DTBs, but I haven't used it. I found it a lot easier to just hard code, move on, and improve on this later. And actually, the fact that I'm hard coding kind of does limit me a little bit because, for example, when I upgrade to the Raspberry Pi 5, most likely the base of the MMIO is going to be wrong and I'm going to have to recalculate it. But that's a problem for future me. Except I'm probably going to start doing it soon after I record this video, so it's a problem for very near future me. But hey, it's not current me, so let's move on. Now, for example, if we want to access UART, which is what we have been using for console output so we can see what's happening on our system, then we're going to be using the MMIO base plus an offset that's specified for UART. If we use that, we should be able to get UART output. And so I try, and it looks like this. Technically, the output is there. It is showing what I think it should be showing, but it looks weird. And also, I actually did this based on some sample code from the OS Dev Wiki on a different project, just so I could test it out on a completely clean project and then ported it to my own project. So the log that you're seeing here is not really a log from my operating system, but rather from this separate sample project that I used. But really, what I'm saying here applies to everything. Now, the problem that we're seeing here is multi-threading. Our CPU isn't just one CPU. Internally, it's actually 4 different CPUs all working completely in parallel. And all of them just so happen to be executing our kernel code, which means that all of them are emulating our kernel separate from each other. Each of them are printing this hello world to the UART device, and it just so happens to come out like that because all 4 of them are trying to write to it at the same time. It took me a bit to figure out this problem because it's actually not mentioned on the OS Dev Wiki for the Raspberry Pi Hello World sample, so I was a little bit surprised by this. But eventually I figured it out. What we have to do is just disable 3 out of the 4 cores. Eventually we'll have only 1 run in our kernel, and now only 1 of them is going to be writing to the UART output, and it's going to look normal. In order to do that, we're going to use a register called the MPIDR EL1. And this register simply indicates which core is currently active. So what we're going to do is at the very beginning of our kernel initialization process, we are going to check which core we're on. And if we're not on core 1, we're just going to run an infinite loop to stall the core. Eventually, we will be using these cores because we probably do want to take full advantage of the hardware on the system. But for the time being, we're just using one and disabling the rest. Now at this point that I have a hello world, it's time to go through my system and see what works and what doesn't. This is a not very comprehensive list of all the features that I have implemented in my operating system. The idea is to go through them and see which ones will need adaptation and which ones won't. So right off the bat, we already know that some of them will not work. The GPU is no longer a VirtIO GPU. We're now going to be using a completely different GPU, and so we're just going to disable any GPU-related code and move on because we know that it won't work. Likewise, the networking driver that I talked about in my last video will also not be available because it's also a VirtIO device. So we'll disable networking. And finally, we're going to disable disk access. That's also using a VirtIO device. So everything we're left with here should work fine. Now, memory allocation and memory protection, there shouldn't have been any issues, any changes to this because they work more or less the same way in my Virt board and my Raspberry Pi, and I specifically made sure to make them as compatible as possible. Now, input is a different case. Both my Virt board and the Raspberry Pi have an XHCI controller for input, specifically for USB, which means I can get input through a USB device with both of them using the same controller and the same driver that I wrote for that controller. But of course, that driver would work over PCI. This one is going to work over MMIO, so we're going to have to make some changes to it, but we do expect it to work. For the time being though, we're going to disable it as well and move on. After that, we have processes, syscalls, and interrupts, which all should work right out the box. Processes and syscalls don't necessarily use any specific hardware, and interrupts, as well as the exceptions that power syscalls, should work the same way in our VirtIO and Raspberry Pi. But when I try to run it, I immediately run into problems with syscalls, and specifically the system crashes. Now the system itself does not really give me any useful information, but QEMU does, and it tells me that the problem is that I'm trying to jump from EL3 to EL0. EL is the exception level, and I talked about exception levels when I talked about memory protection and when I talked about processes themselves, but back then I only talked about exception levels 1 and 0. 0 being the unprivileged exception level, and 1 being the privileged one. But there's actually 2 more exception levels. There's EL2, which is the hypervisor exception level, and it's used for virtual machines. And finally, the secure monitor EL3, which is used for secure operations. To be completely honest, I don't know exactly what these secure operations are, but there is this hyper secure mode. And our Raspberry Pi, when it boots, at least on QEMU, runs entirely in EL3. And we cannot simply jump from EL3 to EL0. We have to make a progressive jump from EL3 to EL2, EL2 to EL1, and EL1 to EL0 once we actually activate some processes. So I needed to adapt my boot code to also do this. And I would show the code here, but to be completely honest, when I wrote the code, I actually was using someone else's code as reference, and I kinda understood what we were doing, but when I went back to look at it for this video, I have no idea what it says anymore. I don't know how that code works. All I know is it works, and that's good enough for me. Now, at this point, the system was working. There wasn't much you could do with it because the GPU was disabled, input, networking, and disk access were disabled, but the system was running without any issues. So now came a very important question. What do I do with the VirtIO board? At first, I considered to just stop supporting it and just support the Raspberry Pi from now on. But I actually decided not to do that and to continue supporting the VirtIO board, and this actually turned out to be a pretty good idea. The main reason I had for doing this is the Virt board has the VirtIO devices over PCI, and this means I've already written most of the code for the driver for any new device that I want to add that's compliant to the VirtIO spec. So it's really easy for me to add new devices and focus on writing whatever functionality comes with these devices inside my operating system rather than writing the drivers for the devices themselves. So this is a pretty big advantage that allows me to prototype something quickly, and so I will continue to use the VirtIO board. But of course, I also want to run this on a real Raspberry Pi and possibly on this emulated Raspberry Pi. So at this point I started working on getting multi-board support so that I could have this running on both boards and work more or less the same way. And this distinction between the two is just a distinction that happens when I'm initializing the kernel. So in my boot.s file, the one that I just said I couldn't really show because I didn't understand the code, but this is a visual representation of what the code does. First, we check the core number. If we're in any core that isn't core 1, then we're just going to go idle by running an infinite loop. That's to prevent the issue with 4 cores trying to run the kernel at the same time. If we are on core 1, then we will execute the kernel. But before we actually get to the kernel code, we're going to check the current exception level. The current exception level could be 3, 2, or 1. And depending on which one it is, we're going to progressively drop from one until the other until we get to exception level 1, at which point we will execute the kernel. And then the kernel itself is going to activate processes, and user level processes are going to be running on EL0, but that's already there for the kernel to deal with. This is the kernel's initialization. But another thing that I needed to change was the entry point into my kernel. This is actually different for both devices, and it's defined in the linker. So I needed to pass a variable to the linker that indicates where the kernel is going to be sitting in memory, so that when the device gets activated and it jumps to the address expecting a kernel, it's actually there and my kernel can run. So now I have multi-board support. You can call make run with mode VirtIO to run the system using the Virt board, and you can make run with mode RPi to run it with the Raspberry Pi 4B. The default between these two is actually Virt because it is a better system for emulation. We're going to talk about the limitations that the Raspberry Pi has on QEMU throughout this video. But if you just call make run without any arguments, it's going to run the Virt board. Okay, so this is what our system looks like right now. We have disabled the GPU, input, networking, disk access, but everything else, now that we've fixed this EL0, EL3 issue, is actually working fine. So now it's time for us to start adapting these devices that we have disabled and re-enable them again. We're going to start with the GPU, same as I did when I first wrote the operating system. So my system already supports 2 different GPUs. First, it supports the VirtIO GPU PCI GPU, and in order to run it, it needs to do several initialization steps. First off, it needs to actually initialize the device, and because this is a VirtIO device, it's done entirely through the common functionality of the VirtIO devices. This is what I meant when I was talking about the fact that a lot of them have common functionality and I don't have to write a lot of the boilerplate initialization driver code. I can just focus on the features. After that, we have to request the display info to know what display is currently connected to this GPU. Then we have to create a resource, attach a backend to that resource, set a scanout to connect the resource to the device, and finally we're going to have a frame buffer connected to our screen. But we're going to need to transfer and flush in order to have the information on that frame buffer show up on the screen. If you want a more comprehensive list of how this works, it's my first ever video. I talk about this and the next GPU as well, which is RAMFB. Because I was having issues initializing VirtIO GPU PCI, I ended up using a simpler GPU called RAMFB. And even though it is a lot simpler, it still requires several initialization steps. First off, we have to find it using the firmware configuration, which is a QEMU specific thing. Then we have to create a frame buffer and a back buffer and copy data from the back buffer to the frame buffer whenever we want to draw to the screen. Again, also covered in the first video. It's a lot simpler, but even then it required several initialization steps. Now, the Raspberry Pi runs a GPU called Video Core. So how does Video Core work? Well, I'm not gonna lie to you, it's a little bit weird. It's actually easy. The way that it's weird definitely works in our favor, but it doesn't change the fact that, at least to me, it's weird. You see, the way that it works on the VirtIO board, and the way that I believe it works on most boards, even real ones, but maybe I'm wrong about this, is our VirtIO board boots and then it initializes whatever devices are connected to it, including the GPU. The way that it works on the Raspberry Pi is different. When the Raspberry Pi boots, the first thing that turns on before even the CPU is turned on is the GPU. The GPU then loads the kernel and enables the CPU. So by the time that the kernel is even considering initializing a GPU and drawing to the screen, the GPU is already up and running. So like I said, this definitely works in our favor. Now, we still have to do certain things. We have to create a frame buffer, a back buffer, and copy data. Kind of similar to what we have to do with the RAM-FB GPU. Now, this GPU, I believe, actually supports more complex graphics than what we currently have, so I may make a video about graphics soon, and I'm definitely not beating the MooKid allegations on this one, but oh well. For the time being, we have to actually communicate with the GPU in order to draw to it. Now, the way that it works for Video Core is actually it creates its own frame buffer and then tells us where it put it. So we just have to request that frame buffer. But the problem is, we can't just talk to the GPU. It doesn't work that way. Instead, we have to use something called a mailbox. Through this mailbox interface, we're going to be able to communicate with the GPU, ask it information about itself and about the display, as well as ask it to create a frame buffer. So in order to do that, we're going to need to send a message that looks like this. I'm not going to lie, I didn't really bother creating some fancy struct to create these messages. It's just an array of 32-bit values. First is the size of the buffer itself, then code 0, which is a request. Then after that, a series of actual requests, followed by a 0 for end. And these requests can look quite weird, but let's break them down. First, we have the property that we're going to be requesting. For example, 48003 is requesting the physical size of the screen. After that, we have the length of the information that we're requesting. That is 8 for 8 bytes, 4 bytes for the width, and 4 bytes for the height. After that, we leave a 0 empty for the response from the GPU. And finally, we actually hardcode the screen size. Now, it definitely wouldn't work this way in the real Raspberry Pi because you can connect it to pretty much any display, and it should work the same way, adapting to the size of the screen. But for the time being, I think QEMU only supports this specific size, so I'm hardcoding it. If I tried any other size, it pretty much crashed. So that's what our message looks like. And then we have to send it to the mailbox interface, which is again located at a specific address in memory. And what we're going to do is just put a pointer to the message that we're sending in a specific channel of this mailbox. In this case, it's channel 8, which I believe is for requesting properties. Not just for the GPU, but for the system as a whole. And after we've done this initial setup, deciding the size of the screen as well as the format of the colors that we're going to be writing with, then we have to actually request a frame buffer. We're going to send another message, this time with just one property, with tag 40001, which the GPU will interpret as create frame buffer, a size of 8, because we're expecting a 64-bit response back, 0, where the response to the mailbox call will be written. And just to clarify, this is a response to the mailbox call, not to the create frame buffer call. So here we will find whether our message succeeded in being sent or not. The actual response to the message will be found in the next value. Currently we're writing 16 because we're asking the GPU to create a 16-bit aligned memory address for the frame buffer. It will overwrite that and the next 0 after that in order to respond back with our GPU frame buffer location in memory. So it's actually a lot simpler to initialize this GPU than even RAM-FB because it creates the frame buffer for us. Now we still need a back buffer because if we draw to the frame buffer while at the same time it is reading from the frame buffer, this can cause issues. I talked about all this in my first video, which was mostly about the GPU. But finally, the GPU is now enabled. After this, the next step I decided to work on was disk access. And disk access is specifically done through SD cards on the Raspberry Pi. If you've ever used a Raspberry Pi, you know that you need to flash an SD card with the operating system or with whatever else you want to have on it, and then plug that SD card into the Raspberry Pi. It doesn't use any SSDs or any fancy drives like that, it just uses an SD card. Now in our Virt board, we were using the VirtIO BLK PCI, a block device which is meant to simulate real disk access. It can access chunks of data called blocks, and the file system that we were accessing was formatted using exFAT. But now, all of that has to change. First off, we're going to be using a completely different controller called the SDHCI. Then, we're not going to be using block devices anymore, but rather the SD card. Although internally it works the same way, it is technically a different device. And finally, technically, we can still work with exFAT, but once we try to run on real hardware, like I said, the GPU actually initializes the Raspberry Pi, and it is going to look at the SD card to find our kernel. And if the format isn't FAT32, it will not find it. So our format, at least for the boot partition, needs to be FAT32. But I don't support partitions yet, so for the time being, let's just say our entire disk has to be formatted with FAT32. Now let's talk about using the SD card itself. So we're going to do that through the SDHCI, which again is mapped to memory, and its configuration looks like this. It's a lot of registers, but specifically we care about these here. We care about the command and transfer mode register. We care about 4 response registers, the data register, 2 control registers called control 0 and control 1, and an interrupt register. Before we see how these registers are used, let's just quickly initialize the device. We're going to do that by writing a 1 to bit 24 of the control 1, which is asking for a reset. Then we're going to enable power to the SD card reader by writing F shifted by 8 to control 0. Then we're going to have to set up the clock, and this is a similar situation to the initialization code. I used some other code as reference, and as a matter of fact, the code that I used as reference was using other code as reference, and even he said he didn't fully understand the code that he was looking at, he just copied and pasted it. And even though I tried to not just blindly copy and paste, I sorta understood what I was doing while I was doing it, and I definitely didn't understand it at the time of making this video, so I'm skipping over this. We just have to set up the clock because pretty much every peripheral and our system itself runs on a clock system, and everything needs to be synchronized. So what we're doing is making sure that the SD card and our system are synchronized. After we've done that vaguely defined task, we will be able to issue commands to the card and the controller, at which point we will be able to control it, set up the SD card, and transfer data from it. So let's look at these commands. This is where the command transfer mode register comes in. This is actually 2 different registers, the command register and the transfer mode register. In the command, we're going to define what it is that we're trying to do, and the transfer mode simply indicates information such as the direction of our transfer, whether we're sending data or receiving data, as well as the transfer size. But what do these commands actually look like? Well, commands are actually numbered, and based on which number you write to the command register, you're running a different command. So command 0 is the go idle command. This is essentially just resetting the controller back to a neutral state. And it's the first command that we should issue. After that, we'll want to send the command 8, which is the interface condition command. I'm not gonna lie, I'm not super familiar with how this command works and what information it gives us, because this command can actually fail, and that's okay. It just means that our card is an older card, and that's the case for the QEMU card that I was using, so I never found out what this command was really used for. All I know is it times out, and I can just move on from that. Then there's command 55, the application command. Now this command itself doesn't really do anything, but different SD cards have different functionality, and that functionality is accessed through application commands. Whenever we send a command preceded by command 55, then we will be sending an application command. And so we will be sending command 55 followed by command 41, or application command 41, which is specific to the type of card that we're using. Which again, I believe we determined by timing out of command 8, but don't quote me on that. Application command 41 is accessing the operating conditions register. We're simply asking the SD card what voltages it works at to know if it's compatible with the voltages that our SD card reader works with. I do believe that maybe the interface condition is doing that for newer cards, but I'm not sure. After that, we can send the command 2, which is send card ID. The card will simply give us its ID, and we will use it to know which card we're working with. After that, we're gonna send command 3, which is the relative card address. Now, the card ID is the identifier for the specific card that we have in the reader, but we probably don't need this for anything besides just identifying the card that we're working with, but what we really want is for the card to send us its relative card address, because through that we will be able to talk to this card directly. Now, I don't know if this means that hypothetically there can be multiple SD card slots for a single controller, because I don't think I've ever seen multiple SD card slots, but maybe that's a thing that I just don't know about. Either way, the relative card address is going to help us to talk to this specific card from now on. And of course, we're going to have to select that card using command 7. We will send here the relative card address in order to let the controller know that from now on we will be talking to this card. At this point, we're ready to do transfers between the card and our system. But before we do that, we're going to have to send command 16, which is set block length. I talked about how our previous system was a block device, and it worked by retrieving or writing chunks of data called blocks. This is simply specifying how big each block is. And because we will be using this SD card as a mass storage device, we will be setting it to 512. After that, we're finally ready to start reading from the disk. We're going to send command 17 to read a single block, or command 18 to read multiple blocks together. We're not going to be doing writing just yet. As it is right now, my system has nothing to write to the disk, so I'm not too concerned about doing that, and honestly, I'm dreading considering writing for exFAT or FAT32. Now, before we move on, let's talk about how we actually retrieve this data. We have a register called data, and I mentioned that this is the one that we're going to be using to transfer data, but this is not a pointer to a buffer or anything like that. This is a first in, first out register. That is to say, whenever we're requesting data from the device, it will send the data here 32 bits at a time, or 4 bytes at a time. And we have 512 bytes for just one block, that is one sector of the disk. And as a matter of fact, both exFAT and FAT32 work in clusters, which are multiple sectors, so this is actually quite slow. There is technically DMA, which is direct memory access, and it does work with buffers, so it's a lot faster, but I couldn't really find a way to enable it, at least just yet I haven't been able to, and the reference code that I used didn't use DMA, so for the time being that's not active on my system, and I just have to read the data 4 bytes at a time. But with that being said, let's move on to FAT32. Actually, you know what, let's take a little break. Let's just complain about Microsoft. Let's just get it all out of my system, because FAT32 was created by Microsoft and it's even worse than exFAT, and Microsoft is just so... Whew, that felt good. Okay, let's talk about FAT32. So I talked about exFAT when I talked about processes, because we wanted to load processes from the disk. And I talked about how poorly implemented exFAT is, how little they have thought it out, and how bad the spec is. Well, exFAT is actually an evolution of FAT32. Not only that, but it's actually a complete remake of the file system from the ground up. Now, FAT32 is not like that, because FAT32 is actually based on FAT16, which itself is based on FAT12. Microsoft is actually very much about backwards compatibility, so these file systems are kind of built on top of each other. exFAT is not like that at all. exFAT is built entirely different, so it's not super compatible with these 3 file systems, but it has a bunch of improvements. All this to say, the one that I complained so much about is actually the improved version, and one that made Microsoft say, guys, you know what? We should probably just scrap this whole thing and do it from scratch, because something's gone wrong along the way. And I'm dreading working with FAT32 if it was so bad that it made them want to scrap it and start over. Now, obviously the product that they started over is also bad, but trust me, it's not as bad as this one. Okay, let's get into it. I know I said I wasn't going to complain about Microsoft and I got it all out of my system in the previous section, but I just cannot stop. Let's begin. This is what a file entry looks like in FAT32. A single file has all this information. It looks like a lot, but really it's not. We start with the file name. In exFAT, we started with an ID that identified this as a file entry. Now, the spec didn't actually tell us what that ID was, we had to kind of guess it, but at the very least, it told us an ID that identified this as a file entry. Here we start immediately with the file name, and I guess you can just guess that this is a file entry. The file name is 11 bytes, 8 bytes or 8 characters for the name of the file, and 3 for the extension of the file. But what about files that are more than 8 characters or more than 3 characters in the extension? Don't worry, we'll get to them. For the time being, we're limited to only 11 characters. After them, we have the flags. These are very similar to the flags in exFAT. They indicate whether a file is read-only, it's hidden, it's a directory, and the last one indicates whether it has a long file name, so if it's longer than the 11 characters that we just found. After that, we have a reserved byte, but I believe that it is used to determine case sensitivity because for whatever reason, the file name is always uppercase. Don't ask me why, but I guess this can be used to determine case. After that, we have timestamp data. We start with the 10 millisecond increment at which the file was created. So honestly, I don't do anything with this data, so I don't know what it looks like in practice, but I think it's an increment of fractions of a second in which the file was created. That is to say, we have a lot of information about when the file was created. After that, we have the timestamp in hours, minutes, and seconds, but the seconds have to be multiplied by 2. Why by 2? Why multiplied at all? I don't know, ask Bill Gates, don't ask me. After that, we have the date in which the file was created. So like I said, we have a lot of information about the creation of the file. Then we have the last accessed date. What about the timestamp? What about the 10 millisecond increments? I don't know, ask Bill Gates, don't ask me. I don't know where that information is. For some reason, they just decided that we don't need to know when within a day a file was accessed. We are just okay with knowing that it was accessed on a specific day. After that, we have the first bits of the cluster where the data for this file or directory is located. In exFAT, this was just one register that we could look at to know where to go find the file or folder. Here instead, it's divided into the high bits and the low bits. Now, this I do understand why it does that division, and actually they're not even continuous in memory. They're separated by the modification time and date, but I believe most likely that's because FAT16 and FAT12 were not using 32 bits. And so this is a new addition to FAT32 and they just used whichever register was available, most likely a reserved register. Although maybe it could also have been the last accessed timestamp, which is why we don't have that register anymore. I have no idea. But this is the first bits of the first cluster of this file or folder. After that, we have the last modified time and date. Here we have both. And then we have the low bits of the first cluster. And then we have the file size. This is a 32-bit value and it is only valid for files. In exFAT, this would tell us the size of a file or a folder. In FAT32, it only tells us the size of files. It doesn't tell us the size of folders. So if we find a structure that looks like this, and we can just kind of guess that we found a structure that looks like this because there's nothing to identify it with really, at least not to my knowledge, then we know that we found a file. But like I said before, we're only limited to 11 characters in the file name. So that's where the long file entries come in. They look like this. They have an order, a name1, which is 5 16-bit characters, then attributes, long type, which indicates that this is a long file name. We have to look at this value and compare it against a specific value to know that we're looking at a long file name. This one does have an identifier. It's just not at the beginning. Then it has a checksum. Then it has name2, which is another 16-bit 6 characters. Then we have a reserved value and 2 more 16-bit name characters called name3. So whenever we find one of these entries, we're going to need to combine the data that we find in name1, name2, and name3, which are not continuous in memory, to figure out the file name. But there can actually be multiple long file name structures, I believe for a total of 255 characters. So are they continuous in memory? Well, actually the answer here is yes, but backwards. And also they precede the file entry. So it looks like this. If you have 4 long file name entries for a specific file, you will find the 4th one, then the 3rd one, then the 2nd one, then the 1st one, and finally you will find the actual file entry. Say what you will about Microsoft, but they know how to build anticipation. So besides this, the way that we actually access the data on each system works more or less the same. I was actually able to just copy my exFAT driver and make these changes into it to transform it into a FAT32 driver. And technically this wasn't necessary because, like I said, on QEMU, the SD card can just have whatever we want on it. But on an actual Raspberry Pi, it's going to need to be formatted in FAT32. So I'm getting ahead of myself a little bit here, but it's useful. Let's move on to input. Input should have been the easy one. Both the Raspberry Pi and my vert board use XHCI. the extended host controller interface for USB. The problem is, this interface is not emulated on QEMU. Instead, QEMU emulates the older interface on the Raspberry Pi, DWC2. Just when I thought things were looking good. Now, the good news is, a lot of the way that we work with USB devices is going to be the same because the USB standard is separate from the controller standard, and I've already implemented plenty from it. So plenty of the code that I have for input can be reused, but the code for the actual controller needs to be rewritten. First off, we're going to need to perform a power reset on the controller by writing to its MMIO base plus offset E00. We write a 0 to that to reset power. After that, we reset the actual device by writing to the to the global reset control. Yeah, that makes more sense. We write a 1 to that, which resets the device. Then we have to write to the the global AHP configuration, which is the high performance bus configuration. And this will actually allow us to enable DMA. So remember how I said that my SD card controller is really slow because we have to read bytes 4 at a time? Well, we're not going to have this problem here because we have DMA. We just use a buffer, we just tell the device where to find that buffer, and it will either read from it or write to it, all at once and not 4 bytes at a time. Once we've done that, we're done configuring the device, but we need to configure the port. And yes, that's port singular. I don't know if it's this way in a Raspberry Pi, most likely not because it does have multiple USB ports, but DWC2 on QEMU has only one port, which means only one device can be connected to it. Now, in order to access that port, we first need to enable its power. We do that by writing to bit 12 of the port. Then, the steps for configuring the device are pretty much the same as they were on XHCI, because like I said, this has to do with USB, not really with the controller, and so it's already done. First off, we need to reset the port, then the device will become available to talk to. We will be able to request its descriptor, which will give us non-human readable information about the device. We can optionally request string descriptors, which will give us human readable information on the device. Then we can request the configuration descriptor, which will tell us how to configure the device, at which point we can actually configure the device through its endpoints. But we try to do that, and the device looks like this. It's not the keyboard that I was expecting and that I plugged into my QEMU instance, but rather it's a USB hub. This is a device that has multiple USB ports on it, which allows you to connect more devices if you don't have enough ports on your computer. And actually, we only have one device connected, which is the keyboard, but QEMU automatically adds a hub because it knows that the DWC2 controller only has one port, and so it preemptively includes a hub so you can connect more devices through that hub. But that means we need to actually support the hub now. And let's talk about how to properly communicate with a USB device over DWC2, because then we will understand how to work with the hub. DWC2 works with channels, whereas XHCI worked with transfer rings. A channel looks like this. It's not a whole lot of information. We have a register called CHAR, or the channel characteristics. This is the register that we're going to be using to know which device we're talking to, which endpoint on that device we're talking to, as well as to send commands to the device, all done using this register. Then we have the split register. The split register is what we're going to be using to communicate to a device that's on a hub. In the channel register, we're going to specify which device and which endpoint on that device we're going to be talking to, and in the split, we're going to be specifying how to access that device through a hub by specifying the hub's address and port. Then we have the somewhat deceptively named interrupt register. This is not interrupt in the sense that I've been talking about interrupts in this series. It's more so of a status register. We can use this one to know when our commands are completed, when there's been an error, what type of error that's been, and so on. And then we have the interrupt mask, which simply allows us to enable or disable these interrupts. After that, we have the transfer size, and this simply indicates how much data we're going to be transferring between the device and our system. And finally, the DMA register. The DMA register is the one that we're going to be writing a pointer to a buffer to in order to communicate using DMA, which, like I said before, is a lot faster. So let's see this in action. Let's say that we have 3 channels, although really we have more than that. So we're going to initialize our device, we're going to reset the only port that we have, and we're going to find a USB hub on it. Once the port is reset, whatever device is connected to it will become available on channel 0. Now, channel 0 should always be left open for other devices to also use when they become available. So the first thing we're going to do is we're going to address the device, give it a proper address, and we're going to move it to channel 1. Then we're going to go through the entire configuration steps that I talked about earlier and in my input video, and we will find out that this is a hub. So we're going to go through its ports, see if there's any devices connected to them, and reset those ports, at which point those devices will become connected to channel 0. And this is where the split comes in. Currently, we're communicating with our keyboard on channel 0 because we haven't addressed it yet, and like I said, it by default will communicate through channel 0. But in order to communicate with it and not with the hub again, we have to use the split register to specify we're going to be talking to the keyboard through device 1, which is the hub, and its first port, port 1. So likewise, for the keyboard, we're going to address it and move it to channel 2, at which point we're going to configure the device itself, and this will actually lead us to use channel 3 in order to enable its endpoint, which is how we're actually going to be receiving data from the keyboard. And again, for both channel 2 and channel 3, which are the control channel and endpoint 1 channel, for the keyboard, we have to use the same split in order to communicate with it and not with the USB hub. Now, that's pretty much all the changes that I needed to make to my system, but they have some major limitations. First off, there's no networking. You'll notice that I didn't talk about networking, even though that was the topic of my last video. Now, QEMU actually does not emulate the Raspberry Pi's controller for networking. The Raspberry Pi has its own network controller. Technically, I could do networking using the USB networking device that QEMU provides. And I actually have one of those lying around, so maybe I would be able to write code that works on both QEMU and the Raspberry Pi. But I'm not super interested in doing this because if I connect through Wi-Fi on a real Raspberry Pi, I'm going to need to figure out how to actually connect to a Wi-Fi network using a password and encryption and a bunch of other complicated stuff like that that I'm not really interested in doing right now. And especially not when I'm first trying to work with a new hardware. So for the time being, there's no networking on this. Once I'm actually running on a real Raspberry Pi, I will be writing a driver for the real Raspberry Pi's networking, which also has Ethernet, and that will allow me to skip the whole password setup to connect to the router thing. Besides that, we don't have interrupts for input. You'll notice that I mentioned interrupts, but that was for a register that's more so used for status. We don't have interrupts in the sense that when you press a key, the execution of the current program stops, the key is handled, and then the execution of the program resumes. We don't have that, and so we have to poll. Every once in a while, we have to check if a new key has been sent, and the device will tell us whether it has or not. This is very slow. It does lead to severe input lag, but as far as I know, interrupts are not supported by this controller. Then, there's no customization for screen size. Like I said, for some reason, QEMU only allows me to have a 640 by 480 screen size. If I try any other screen size, it just crashes the entire system. And finally, we don't have DMA for the SD card. So, SD card transfers are very slow. And at the very least, we're going to be reading 512 bytes in 4-byte increments. But really, we're going to be working with FAT32, in which most likely we won't be retrieving a single sector, but rather a group of sectors, because FAT32 works in clusters, which means a lot of data, 4 bytes at a time. It's quite slow. It takes a couple seconds to load what should be my Raspberry Pi SD card's root directory. So all of these things actually mean that my Raspberry Pi emulation is quite slow and is missing one major feature, which is networking, although that's by choice. But you know what else is slow and has mailboxes? That's right, the post office, am I right? Okay, boomer jokes aside, that's the end of the video. Now, I actually did get a Raspberry Pi 5 recently, a couple days ago, so I will be looking into how to port it to that. I am both looking forward to having my system run on real hardware and not looking forward to porting it to real hardware. At the same time, before I've even considered running my own operating system on that Raspberry Pi, I've been running Raspberry Pi OS on it and learning how to debug using UART. So far, because I've been working with QEMU, the UART output is routed directly through QEMU to my terminal. But if I'm going to be running on real hardware, I'm not going to be able to do that. I'm going to need to use one of these USB devices connected to the Raspberry Pi in order to see UART output. And as a matter of fact, I was having issues setting these up, but the reason is because the Raspberry Pi actually has 2 ways of getting UART output, through a dedicated port or through GPIO ports, and you have to specify which one. So it wasn't much of an issue, but I'm glad I figured it out when I was using an already fully built operating system. specifically for the Raspberry Pi rather than debugging this while also working on my own operating system when I wouldn't have known where the issue was, whether in the operating system or in the hardware. With that being said, I don't know if I will be making a dedicated video to porting to hardware on the Raspberry Pi. I'm considering the idea, but I'm not sure about it yet. And honestly, this video covers most of what I'm gonna be doing anyway. Just now I'm gonna be porting all of that I just did to a real hardware device. Besides that, the operating system is actually in a pretty good place where I can start considering other projects. And of course, last week I published the networking video, which was the first of those projects that I asked you about, but honestly, I've been considering some other things to do. First off, I am considering doing some graphics programming, maybe even a game engine, and honestly, I'm considering participating in some game jams this summer, so maybe I will be creating my own game engine, or maybe I will just be using Unity or Unreal because I'm already familiar with them and they take away a lot of the work. But either way, I'm definitely interested in making my own game engine and expanding my graphics knowledge, so I will be doing that at some point or another. There's also plenty of places in which I need to optimize the system, improve on it, make it more robust, more reliable, so there's plenty of optimizations that are not really video worthy because they're not flashy or interesting new features, but they're still important to do. Now that I know more about operating system architecture, I can actually start considering what I want the architecture for my system to look like. And obviously I've already built a system, or a large part of it anyway, and it's in a monolithic architecture, but I am considering maybe porting it to a more modular style, as well as just exploring that in general. And finally, I'm also considering doing some audio stuff, so that I can have audio output on the system. Now, I know that these are not necessarily aligned with the poll that I asked a while ago as to what I should work on next. The winner of that poll was networking, which I've already done, but the second one was a compiler. But to be honest, when it comes to a compiler, it wouldn't really add anything of value to my system. I already have a compiler and it works perfectly fine. So building a new one just to replace one that works perfectly fine is not really my top priority right now. I do want to build a compiler, but maybe not just yet. And also from now on, videos will almost definitely slow down because I need to do all of these things which are not fancy, flashy things. But I will continue to post videos about this system. I will continue to post videos about other projects that I will be working on. And for the time being, that's the end of the video.